Okay, welcome everyone to the Rapid Interactive Session, Control of Aerospace and Biological Systems. Many of you have probably been to the Rapid Interactive Sessions earlier this week on Wednesday and Thursday, but just go over the overall structure of the session. So first we'll be meeting in this Zoom room until 11 o'clock. We'll start with our keynote presentation, followed by 21 rapid 3-minute presentations. And then we'll move on to the interactive portion of the session where each of the presenters has their own Zoom room. That's at 11 o'clock. So you'll need to go back to the main conference program and find the Zoom link in there to go and have further discussion with particular talks that you're most interested in. So if you're presenting in the session, also you should be sure to go to your Zoom room at 11 o'clock today. But first, we're going to start off with our keynote presentation, and that's by Dimitris Coleman from Michigan State University. He'll be presenting the paper Backstepping Control of Gliding Robotic Fish for Trajectory Tracking in 3D Space. This paper is by Dimitris Coleman and Jiabo Tan from Michigan State. So we're going to play his video, but please do use the Q&A feature. You can find at the bottom of the Zoom window so that he can be answering your questions throughout the talk, and then we'll also have time for live questions after the talk. Thank you.
Hello, my name is Dimitris Coleman. I'm a third-year PhD student at Michigan State University. I work in the Smart Microsystems Lab under Dr. Jiabo Tan, and today I'll be presenting my work on control of gliding robotic fish. Gliding robotic fish belong to a class of underwater vehicles called underwater gliders. These are autonomous, buoyancy-propelled vehicles that achieve forward motion through a combination of modulating pitch and changing the depth. They can be steered through control surfaces, such as a rudder, or by shifting weight internally to induce a roll angle. Gliders are known for their energy-efficient gliding and spiraling motions, allowing them to operate for weeks at a time. And over the past few decades, they've become valuable tools in a variety of applications, as seen here on screen. Gliding robotic fish combine the energy efficiency of underwater gliders with design concepts from tail-actuated robotic fish to achieve high maneuverability. For perspective, the original glider design with internal mass turning mechanisms typically have a turn radius between 30 and 50 meters and can achieve around 7 meters with a rudder. In contrast, the robotic fish can achieve a turn radius on the order of 1 meter, making it better suited for smaller, more cluttered environments. The robotic fish has 3 servo control actuators. The first is a linear actuator to pump water in and out of an internal syringe. The second is a linear actuator that moves the mass along the body so the robot can pitch up and down. And the third is a servo motor that controls the tail angle of the robot. In the past, we've used this robot to monitor harmful algae blooms, and more recently, we've used it as an acoustic telemetry platform in preparation for fish tracking applications. In this work, we're interested in control of the gliding robotic's energy-efficient gliding motion. Glider control is difficult due to the highly nonlinear dynamics that represent its motion and under actuation. It can't move forward without changing depth, and it can't turn unless it's moving forward. For our fish, control has been primarily done for depth control using PID and open loop pitch control. We've also done waypoint tracking and control of steady state spiral paths. Previous work in underwater glider control can also be applied to the robotic fish, but most of this control literature focuses on control designs to reach desired pitch angle, velocity, depth, or steady state gliding paths. 3D motion control is scarce, likely because gliders usually operate in the open ocean and only need to be concerned with the planar gliding profiles. However, this robot is capable of maneuvering through smaller, more complex environments, making fine-grained trajectory tracking more relevant. And in this work, we specifically look at the problem of tracking a time-varying reference position and pitch angle in 3D under only gliding motion. We include the pitch angle because it plays a significant role in the motion of the robotic fish. In this work, we solve an underactuated tracking problem by exploiting the pitch angle's effect on the horizontal motion dynamics using a hybrid error function. Then we use backstepping control to stabilize this error. And we use 2 time scale analysis to illustrate how the original tracking objective is achieved. Before we get into details, let's go over the motion model, which has 12 states, the XYZ position, and yaw pitch roll Euler angles represented in the inertial frame A, as well as the body fixed linear and angular velocities represented in the body fixed frame denoted by O and the blue axis XB, YB, ZB. It has 3 controls. The first is M0, the net buoyancy of the system, which allows us to sink or float. The second is RP1, the position of the movable mass along the body fixed XB axis with respect to the geometric center of the robot, which influences the pitch, and the tail angle delta, which influences the yaw. These are the dynamics, the first 2 equations being the kinematics, mapping the linear and angular body fixed velocities to their inertial counterparts. The second 2 are the dynamics, which are taken from Zhang 2014 and explained in detail there. Here, we'll just focus on the structure of the dynamics, emphasizing the control inputs. Now, revisiting our control objective, we formulate the error vector PE, which is the difference between our position and pitch angle and their desired values. This leaves us with 4 variables to be controlled, but only 3 control inputs. To handle this underactuation, we start by transforming the Cartesian error coordinates into an equivalent cylindrical representation by representing the vectors XE and YE in the inertial frame with a magnitude rho E and angle eta as shown in the picture to the right. Next, we use this cylindrical representation of PE to construct an augmented error vector PEA with reduced dimension to match our dimension of our control signals. This includes the yaw error, psi e, the hybrid error function xi, and the depth error, ze. Looking from a bird's eye view, you can see that psi e is a heading error, and it serves to align the fish heading, psi, with in the direction of the vector rho e, pointing from the fish position to the desired position. The error function xi combines the pitch error theta e along with a function of the pitch angle and the position error vector projected onto the robotic fish's body fixed x-axis. Now we choose to use backstepping to stabilize the error vector PEA. Backstepping is a well-known procedure that allows one to design a nonlinear controller while constructing a stabilizing Lyapunov function. And according to Lyapunov stability theory, showing that the derivative of the Lyapunov function is negative definite guarantees stability of your nonlinear system. And after going through the backstepping methodology, we get the following Lyapunov function. which is a function of our error states from the vector PEA, and these new states zeta, which we define as the difference between the derivative of our error states and some desired stabilizing value. After that, the derivative of the Lyapunov function can be expressed as seen here. And from this step, because zeta dot is a function of our inputs, we can design the input such that zeta dot stabilizes the entire system. And once these values of minus ki zeta I are met, we get the following negative definite Lyapunov function with a little bit of algebra. And this guarantees that the backstepping controller drives our errors to zero. Now, the control design analysis guarantees that the errors in the vector PEA all go to zero. However, the original control objective was to send the errors in the vector PE to zero. We can show this using timescale analysis. And timescale analysis is a model reduction technique from singular perturbation theory. It allows us to separate the system into fast and slow dynamics. And one major component is that we can analyze them separately to help prove stability of the entire systems. In essence, it lets us analyze what happens to the slow dynamics associated with PE when the fast dynamics associated with PEA goes to zero. Following this logic, we use this image to depict the pitch angle of the robot when the errors theta E and xi are equal to zero. Now, PEA equals zero means that the robot is pointed in the desired direction and moving at the desired depth rate. In this situation, theta E would leave the position offset error constant. However, xi equals zero would give us this expression for the pitch angle, which in essence perturbs the pitch angle slightly from the desired pitch angle, so that the actual position and orientation of the robot will slowly catch up to the desired position and orientation as they ascend at the same rate. So in essence, what the hybrid function is doing is sacrificing some pitch tracking accuracy in order to minimize the position error. And likewise, it can be seen to do so in other situations. The controller will simulate and simulate with an observer to determine the body fixed linear velocities, because in general, this is something that we can't measure with the robotic fish. The trajectories shown here were chosen to evaluate the performance of the backstepping controller and compare it against a PID controller. And this PID controller was designed using the same error vector, PEA, that was used to design the backstepping controller. In each of these figures, you see three curves: the reference trajectory in yellow, the backstepping controller in blue, and the PID in red. And the left and top right figures, the PID and backstepping controller performance are fairly similar, but in the bottom right, in the spiral trajectory, the backstepping controller outperforms the PID. This slide animates the backstepping control performance on the spiral trajectory, and these two ellipsoids that you see are the desired position and orientation of the robot and the actual position and orientation of the robot. Here, the backstepping tracking errors shown in blue are compared with the PID tracking errors shown in red. In each of these plots, the backstepping controller minimizes the error to area around zero, while the PID will eventually do it, but isn't able to within the time frame. Here, the backstepping control signals shown in blue are compared with the PID control signals shown in red. The thing to notice here is the chattering. This is due to a discontinuity put in the controller to avoid singularity when the position errors are 0 and the heading error becomes undefined. The chattering is achievable but unwanted since energy use is associated with the derivative of the inputs. The PID controller doesn't see this chattering effect because in the simulation it never minimized the error to an area around 0, but from other simulations we can see that it also will experience this same chattering effect. In conclusion, we designed a controller for the gliding robotic fish to track a 3D position and pitch angle using a hybrid error function. For future work, we would like to establish a more rigorous proof of convergence through two-timescale analysis, refine the control design to address the chattering seen in the simulation, and validate the control design experimentally on the gliding robotic fish. Finally, we would like to acknowledge the NSF and Rose Graduate Fellowship Fund for supporting this research.
Okay, great, thank you. Okay, we have some time now for questions. So I see one here coming up. Why were the two different stability analyses necessary? And what aspect did the Lyapunov stability proof not cover? So maybe, Demetrius, you can answer those live.
Yes. So the two different Lyapunov, or the two different stability analyses were needed because the Lyapunov analysis proved the stability of our augmented error vector that contained only these three hybrid error functions that we defined based on our original error. It didn't prove that these errors actually go to 0. And what we see when we do the analysis is that this error still exists in the original objective, but it asymptotically goes to 0 while the augmented vector is 0. And the second question, why didn't you consider the heading angle instead of the pitch angle? That'll be quite. So the reason that we chose the pitch angle instead of the yaw angle is because changing the pitch angle has some more effect on the forward velocity of the gliding robotic fish. So in airplanes, there's this quantity called the glide angle. And it's basically a ratio between the vertical and horizontal distance. And once you change the pitch angle, we indirectly affect this, which speeds the trajectory, speeds the speed of the glider up to catch up with the actual position. Have you considered averaging based methods to address the two time scales? No, this is not something I've considered. I'm not really sure as why we would need to consider averaging based methods for it. If you could explain a little bit more behind the reasoning behind your question. Flight path angle, not the pitch angle.
Maybe you two can talk about it offline too. If Christy wants to send some clarification. How was the settling time consistent between trajectories? If not, how did it change?
So the settling time changes with the parameter and the hybrid function. It's basically a user-defined gain, essentially, that tells you how much control authority you want to give to the position tracking error from the pitch control. And, yeah.
Okay, to what extent can we trust PID for this type of system control?
To what extent can, so PID does pretty well. The only thing is you have to tune it for the kind of trajectories that you want to follow. So instead it'll perform good on the trajectories that you tuned it for and not general trajectory.
Okay, great. Well, thank you so much.
Thank you.
And now we'll move on to our rapid presentations. So we'll have 21 3-minute presentations back to back. So we're not going to have questions for those, but you should check in at 11 o'clock then with the individual Zoom rooms for all the presenters. And Demetrius will also have a Zoom room. So there'll be 22 Zoom rooms at 11 o'clock for interaction.
Hi everyone, my name is Ken Gusinga. I will give a brief overview of our paper titled Noise Analysis in Biochemical Complex Formation from Stochastically Produced Components. This work was done in Dr. Abhi Singh's lab at University of Delaware. Both me and Jikai, who is the first author on this paper, are Dr. Abhi Singh's former students. Complex formation is the process where proteins form dimers or multimers. There are two types of complexes, homomers, which are made of a single species, and heteromers, which are made of multiple species. I'm showing an example of a homomer where a complex Z is made of a single species X, and heteromer where two species X and Y make the complex Z. Complexes are widely used in biological systems. Some examples are choline and anticholine dimers of bacterial virus phase lambda, and G proteins in signaling pathways across organisms are made up of 3 subunits, alpha, beta, and gamma. Because of their functional relevance, abundances of constituents of complexes are tightly regulated. Intuitively, too few of a constituent would result in insufficient complexes for biological function. In contrast, too many would result in waste of resources, to say the least, or worse, could result in detrimental effects. In this work, we ask whether complex formation has any effect on noise. To this end, we use a stochastic model of the complex formation process and apply the linear noise approximation method to compute the moments. We quantify noise from these moments using the Fano factor, which is variance divided by mean. The Fano factor is 1 for a Poisson process, which is the case if a species is produced and degraded, but it does not form a complex, and we take this case as a control. We studied the effect of the order of complex on its noise. In other words, we asked whether dimers have different noise. We found that dimers have higher noise in primers, which have higher noise than tetramers, suggesting that higher order complexes have less noise. Moreover, we also investigated the effect of relative stability of the complex with respect to its constituents. We found that the noise is less if the complex is unstable in comparison with its constituent. With that, I would like to thank you for your time. Please stop by the interactive poster session if you have any questions, comments, or would like to discuss the results in detail.
Hi, I'm Vishal from Michigan State University, and I'm going to present on SIS epidemic model under mobility on multilayer networks. SIS model is a fairly well-studied epidemic model where the entire population is divided into 2 compartments. An individual can either be susceptible or infected, and A susceptible individual can become infected at a infection rate, which is beta here, and an infected individual can transition to being susceptible at the curing rate delta. Now, this model has a key assumption that it only caters to single patch, which is homogeneous and well mixed. Now, what will happen if we relax this homogeneity condition? Now, in this study, we consider heterogeneous system where we allow different patches to have different infection and curing rates. These patches could be different cities, and also we consider different classes of individuals within each of these patch. Now, these different classes cater to different mobility patterns of the population. Now, what we get is a multi-layer network of subpopulations where the epidemic is spreading at each of the node, but the mobility is happening on each of the layers of the multi-layer network. As you can see from the equations, the first equation here describes the mobility, which is uncoupled for each of the layers, but the epidemic spreading at each of the nodes is coupled through the mobility. Now, we see here two matrices. One is intermixing matrix and the other is mobility matrix. These matrices determine the coupling, and these characterize the population distribution across each layers at a node, and also depend on the transition rate at which the individuals are moving from one node to another. We do rigorous analysis for our epidemic mobility model. First, we rigorously characterize existence, uniqueness, and stability of equilibria. What we find is that there exist two different equilibrium. One is disease-free equilibrium, and the other is endemic equilibrium. We find parameter regimes under which each of these equilibrium are stable. We also find some very simple necessary and simple sufficient conditions under which the disease-free equilibrium is stable. These conditions provide very useful insights into the effect of mobility on the stability of disease-free equilibrium. We also do some simulations and study the effect of different graph structure over different layers. Thank you, and I look forward to seeing you at my poster.
Hello everyone, it's Shara here to talk about a new nonlinear system identification algorithm called causal jump dynamic mode decomposition, motivated by the problem to predict the fitness in bacteria. The fitness of a bacterial population in an environment is their persistence to divide and grow in that environment. Our objective is to develop a database model that can predict the growth curve dynamics of bacteria to estimate their fitness, as opposed to the traditional models which don't extend to new organisms and multiple environmental inputs. To do this, we obtain time series population data of the soil strain Pseudomonas putida by spiking the bacterial culture with impulse inputs of casein and glucose. We use a 96 well plate to vary the two inputs across each well and obtain the optical density of the culture using a plate reader, and this indicates the number of cells in the culture. Our data has a single time series output, the optical density, and two impulse inputs, casein and glucose. Instead of directly tackling the input-output identification problem, we simplify the problem to the identification of a single output initial condition response model. For this purpose, we consider the nonlinear autoregressive model called the NAR model from the system identification literature, which has a single hyperparameter tau that indicates the amount of the past information that is required to make a prediction of the future. By constructing the one-step, two-step, up to tau-step predictors of the NAR model and concatenating them, we can construct a state space model such that we can take any consecutive tau points of the output and predict the output at the next tau points. The Koopman operator converts a nonlinear finite dimensional state space model to a linear infinite dimensional state space model. One of the methods for identifying a Koopman operator is called the dynamic mode decomposition algorithm, also called the DMD algorithm, which in its simplest form involves a matrix inversion of a transform states concatenated from all the data sets. We used extended DMD with monomial basis as a choice of the DMD algorithm, and this has one hyperparameter, which is the highest monomial order for the transform states, and this is denoted by M. This collective method could potentially open the door to a new class of nonlinear system identification algorithms that leverage on the Koopman operator theory. On the 96 well plate reader data, by choosing the tau to be 9 and the m to be 3, we show that we can achieve a mean squared error of 0.034 in the training data and 0.09 in the test. Recently, we collected the high dimensional time series RNA sequencing data from the growth dynamics of the new upcoming industrial microbe, Pseudomonas putida. We are in works to couple this with the growth dynamics plate reader data to identify the pivotal genes correlated with fitness, thereby enabling us to develop a growth harness using CRISPR interference or CRISPR-I to control the persistence of this bacteria in an environment of our choice. Thank you.
Hi, my name is Kate Schweidel. Today I'll be talking about a supervisory control method, and I'll be discussing the method specifically in application to a threat engagement problem. As a case study, we built a Simulink model of a planar engagement, where an interceptor missile is engaging a threat missile, which is attacking some asset. We modeled the interceptor with standard guidance and control, and we use a first-order actuator model. For a threat engagement problem, there are many parameters to select. These may be controller parameters, like gains in the guidance law and autopilot, or physical parameters, like the time and angle at which we launch the interceptor. When we detect a threat, we need to select these action parameters quickly, which means we don't have time to perform thousands of simulations of the full model to determine which actions will perform well for the particular scenario encountered. Whatever action we choose, we'd also like to know the resulting probability of hit, which can inform follow-on decisions such as whether we want to launch a secondary interceptor. The supervisory control problem is described by 3 categories of parameters. There's the scenario S, which is what you know, the action A, which is what you can choose, and the uncertainty theta, which is what you don't know. Given a scenario S, the supervisor needs to select an action A, which can depend on S, which is robust to the uncertainty theta. We can regard the simulation model as a map from the parameters to the hit-miss outcome. This is fundamentally a classification problem, and so we can build a binary classifier offline that also maps the parameters to the outcome and that captures the model behavior with high accuracy. Then, for a particular scenario S, we can optimize over this classifier in real time by maximizing the empirical probability of hit over a finite set of sample uncertainties. We pick the maximizing action A out of a finite set of candidate actions. Note that we evaluate the classifier F bar instead of the true model F. All of these simplifications serve to speed up the optimization. For the case study in this paper, we consider the engagement shown on the right, where the threat T is attacking the asset A and the interceptor I is launched from the origin to try and intercept the threat. The scenario S, what the supervisor knows, is the starting position of the threat, the asset location, and the initial speeds of the threat and interceptor. The action A, what the supervisor gets to choose, is the launch angle of the interceptor and the autopilot crossover frequency. The uncertainty theta describes the threat trajectory. We consider circular arc trajectories where the radius and acceleration values are unknown to the supervisor. We ran 100,000 simulations of the full model offline, which we used to build a neural network classifier with 96.3% test accuracy. Then we used the classifier to compute optimal actions online for several test scenarios. We showed that the classifier-based optimal action significantly outperforms the baseline action, which is an action that does well on average but does not vary with the scenario. Details about the experiment, as well as avenues for future work, can be found in the paper. Thank you.
Today, I will be talking about estimating domains of attraction using finite time Lyapunov functions. In particular, we are interested in solving the problem of finding Lyapunov functions given asymptotic stability for a nonlinear dynamics x dot equals fx. In particular, we are interested in constructive algorithms that can help us in finding domain of attraction estimates and controller design. We use finite time Lyapunov functions for this purpose. So a finite time Lyapunov function can be understood by looking at the classical Lyapunov function definition. The Dickerson condition in the classical Lyapunov functions can be viewed as an infinitesimal version of the Dickerson condition in finite time Lyapunov functions. Recently, a paper by Doban and Lazar showed stability certificates using FTLFs for nonlinear dynamics. We extend their results to provide a constructive algorithm to find out Lyapunov functions. In the interest of time, I will only be talking about the key insights from our theoretical results. From the general Lyapunov function theory, we know that the asymptotic stability of the nonlinear system is equivalent to existence of a Lyapunov function. And we extend this to the existence of finite time Lyapunov function with the particular form for the nonlinear system. And then we connect this to the results in one by giving existence of Lyapunov function Wx for 1, which is analytically derivable. We use these results to find out domain of attraction estimates for a simple toggle switch system, which is a bistable system, which has 2 equilibrium points that are stable. We use the linearized estimate of domain of attraction, which is the standard Lyapunov function theory, to find out the domain of attraction estimates, which are conservative. And when we use our approach based on finite time Lyapunov functions, we find out the new estimates, which you can see are much better than the linearized estimates. Thank you for listening, and I'll be happy to take questions and discuss this in detail in the poster session. I would like to thank my collaborator, Professor Aaron Ames at Caltech, and my general research interests are in using control theory to guide the design of synthetic biological circuits, in particular using model reduction, nonlinear analysis. The code for the paper that I discussed today is available on GitHub with this repository name, and you can find me on Twitter or send me any email with your questions. Thank you so much.
Ladies and gentlemen, we like to present our work with the title Robust Strict Positive Real Control of Variable Stiffness Actuators. This work was a joint effort by co-authors Bernd Wiskeld, Matthias Ilian, Lin Liu, and Steffen Leonhardt from the Institute of Medical Information Technology, RWTH Aachen, Germany. We'd like to motivate our work by the application of rehabilitation robotics. Robot-supported rehabilitation therapy was introduced to achieve, for example, longer training times and higher number of training sessions compared to classical therapy. These robots typically controlled with cascaded impedance control loops, where the controller parameters of the impedance controllers are changed according to patient's state of therapy. However, the interaction of the robot with a highly uncertain and nonlinear dynamical system demands for special control design approaches, which is also the case for us for our exoskeleton application that we are currently building and that you can see in the right-hand figure. So our goal of this research was to parameterize outer loop impedance controllers such that the impedance load transfer function has to have the positive real property. This ensures stability with uncertain and nonlinear passive patient dynamics. However, note that we developed in the following a procedure for the general case. We developed a recursive parameter space procedure for uncertain polynomials, and this procedure employs a MIMO condition for uncertain matrix value transfer function. In the right-hand figure, you can see a graphical simplification. We start by checking positivity conditions for the whole initial parameter space. And then the next step, for example, if we get false, if the condition is false, the space is subsequently divided and checked again, and then this procedure repeats. See the result for our variable stiffness actuator, Mariah, evaluated at different values of physical interaction stiffness KSEE. The goal is a parameterization of our controller values, KD and KP, our impedance controller, which was successfully achieved. Find more details inside the paper. Thank you for your attention.
Good morning, everyone. I'm Loipan Mukherjee, and the work I'm presenting has been done in collaboration with my colleague at the Indian Institute of Technology, Bombay, Professor Shashi Ranjan Kumar. The title of this work is Finite Time Impact Time Guidance Using Deviated Pursuit Against Maneuvering Targets. So why is this particular work important? The primary objective of this guidance scheme, as with any guidance scheme, is to intercept the target. But in addition to that, we also want to impose an impact time constraint. Why is this impact time constraint important? Because often you might be required to take down a much more powerful adversary using multiple smaller interceptors. So simultaneous interception is very important in such cases, which is called a salvo, and therefore we require a tight control over the impact time. Now, most of the work on impact time control has been done on stationary targets in the existing literature. Some have addressed constant velocity targets using the concepts of predicted interception points and deviated pursuit, while others who have, though these works are few, who have considered maneuvering target, they mostly use a radial acceleration component apart from the lateral acceleration one. So our goal is to get rid of these factors, this radial acceleration or the concepts of PIP, and yet be able to intercept a maneuvering target at a desired interception time. So this is the kinematics given for a maneuvering target and a missile combination, and the expression for the time to go for a deviated pursuit based guided missile is given by this. So we shall be also using a deviated pursuit scheme, and the two guidance strategies that we employ, one of them is a continuous time finite time convergence strategy, the other is a sliding mode based discontinuous finite time convergence strategy. The dynamics of TGO can be derived like so, and based on this we have proposed these two guidance schemes. So now we've demonstrated the efficacy of our proposed schemes using some simulations where the simulation parameters are given here. And as a first demonstration, we take a desired interception time of 60 seconds and we show that both these strategies successfully intercept the target, although the way in which the impact time error converges is different for the two strategies, with the discontinuous time strategy calling the discontinuous finite time strategy calling for a sudden change in the variables, although there is not much of a difference in the lateral acceleration commands in the two strategies. In the second case, we now demand a desired impact time of 50 seconds, but with different heading angles of both the interceptors as well as the target, and we see that in either case, both the strategies successfully intercept the target at the desired interception time, again vindicating our success of our strategies. In the final case, we now consider different levels of target maneuver, 4G, 2G, and a non-maneuvering target, and again we see that in all the cases, both our strategies have successfully intercepted the target at the desired interception time of 55 seconds. So there's a lot more to this, but for that you have to tune into the paper, or if you feel like asking us questions, please feel free to drop in queries at these email IDs. Thank you very much.
Hello everyone, I am Abhinav Sinha, a PhD candidate at the Indian Institute of Technology, Bombay, and Dr. Shashi Ranjan Kumar and Dr. Dwaipayan Mukherjee are my doctoral advisors under whose supervision I have conducted this research. Our research focuses on designing guidance strategy for an autonomous vehicle in three-dimensional space under the constraints on its time of arrival. We call this vehicle an interceptor. In practice, engagements are always three-dimensional. In the existing literature on 3D guidance, the strategies were designed by decoupling the 3D engagement geometry into two separate two-dimensional ones. However, one simply cannot decouple the 3D engagement into two separate planar ones if the coupling between the planes is prominent, as this could lead to adverse effect on the guidance performance. So designing an accurate time-constrained 3D guidance is a formidable challenge, and the strategy must ensure a time-constrained interception at any desired time, irrespective of the engagement geometry. Also, it is quite important that the guidance commands do not introduce any singularity in the system. The figure here shows the 3D engagement geometry between an interceptor and a stationary target, assuming that the vehicles are point mass objects. Axes xi, yi, zi denote the inertial frame, while the interceptor's body axes are represented by xm, ym, zn. One can obtain measurements in any frame by simply carrying out a composite rotation using azimuth and elevation angles. The interceptor's velocity, relative range to the target, and effective heading are represented by Vm, R, and sigma respectively. The kinematic equations can be written as the following, which serve as the system for the control inputs AMZ and AMY to be designed. Impact time is the sum of the elapsed time and the time remaining till interception, which is also known as time to go, which is expressed using this relation. By defining the impact time error as a difference between the instantaneous time to go and the desired one, and using the lead angle dynamics, one can write the error dynamics as a sum of nonlinear drift plus a combination of the lateral accelerations in the pitch and yaw directions. Using a finite time control, the error can be driven to zero. However, in doing so, one has infinite choices of AMZ and AMY. We propose a meaningful solution to this by instantaneous minimization of the available lateral acceleration, resulting in non-singular guidance command AMZ and AMY as the following. Now, over these parameters and a final time of 30 seconds, the interceptor arrives at the target from various initial geometries as shown here. And then for the same geometry but different impact times. Thank you.
Welcome audience. Myself is Ranjan Das Gupta, working as a senior scientist at TCS Embedded System and Robotics Lab. Today I would like to present my work about non-singular trajectory control of a pitch-constrained quadrotorcraft using integral barrier Lyapunov function. The proposed work is an improvement of singularity-free hierarchical control using classical VLF-based design. An integral barrier Lyapunov function is introduced to shape the control Lyapunov function as an amalgamation of attitude error and the original attitude constraint in practice. Equation 1 represents the yield dynamics of a quadrotorcraft, where the state vector QV is the pose of the vehicle having 6 degrees of freedom. We can observe that the entire quadrotorcraft system can be decomposed into 2 subsystems, 1 position subsystem and 2 attitude subsystem. It indicates that we need to design a position and an attitude controller simultaneously, separated by time scale. Current slide starts with the description of a position control device. The choice of filter variables in equation 5 and equation 6 are instrumental to provide singularity-free reference attitude calculation. Equation 7 describes the open loop position error dynamics. The term TE is the virtual control error defined and introduced in equation 7 in such a way that a backstepping-like design can be formulated. TT is the saturated virtual compute, desert roll and pitch angles given by equation 16 and 17, where yaw angle is a user-defined free variable. The usefulness of oct and function is to remove sign ambiguity. The attitude error is redefined and an integral barrier Lyapunov function given by equation 23 is considered. Lyapunov function is given by equation 28. Equation 29 represents its time derivative and virtual control inputs are designed. Time derivative of virtual control error gives open loop error dynamics of roll pitch ER rate, and a modified Lyapunov function is defined by equation 31. Finally, the attitude control law is designed, which is given by equation 32, assuming the dynamics is exactly known. This is the main theorem, which states that the overall pose error dynamics is converging asymptotically, provided the gain conditions given by equation 42 and 43 are satisfied. Pitch constraint is satisfied, filter tracking error and auxiliary filter variables are all bounded. Here is the list of parameters that has been used in our simulation. Here is the reference trajectory, which is an involute motion, and observe the performance of the controller in subsequent slides with respect to position and attitude tracking.
Hello everyone, I am Abhinav Sinha, a PhD candidate at the Indian Institute of Technology, Bombay, and Dr. Dwaipayan Mukherjee and Dr. Shashi Ranjan Kumar are my doctoral advisors under whose supervision I have conducted this research. Our research focuses on designing a cooperative guidance strategy for a group of autonomous vehicles or interceptors under the constraint on their time of arrival. There are several advantages of having cooperation among interceptors, such as spatial diversity, redundancy, cost effectiveness, increased efficiency, etc. Further, our strategy is based on a variation of ordinary pursuit, in which the interceptor always looks ahead of the target by a fixed angle, delta, which is shown here in the figure. In doing so, the interceptor takes a relatively shorter trajectory and demands lesser effort than those in the case of an ordinary pursuit. In this work, we also propose a rather unconventional model of interaction. We refer to these as a pseudo-undirected graph of interactions. These pseudo-undirected graphs allow bidirectional information exchange among the interceptor, but the strength in both the directions is not uniform. So this is unlike commonly used undirected or directed graphs. A key feature of using this graph is that each agent or each interceptor has a stake in the consensus value. The next logical step is to evaluate the consensus value over such graphs, which translates to evaluating the left eigenvector corresponding to the null space of the graph Laplacian, which is P here. We proved that the entries of P are all positive. Therefore, the consensus value is the weighted average of the interceptor's initial state. Next, we present the kinematics of engagement for a cooperative simultaneous interception and design the lateral acceleration, which is the control input for each vehicle to arrive at the target together. In this work, we consider a moving target whose design is quite challenging due to motion of the target. So we now demonstrate simultaneous interception by interceptors connected over some special pseudo-undirected graphs, such as in this case, there is a pseudo-undirected cycle with heterogeneous weights, and the interceptor arrives at the target, intercept the moving target simultaneously. Similarly, for a pseudo-undirected star and a pseudo-undirected path. Thank you.
Good morning. I am Dwaipayan Mukherjee. I've done in collaboration with my colleague at the Indian Institute of Technology, Bombay, Professor Shashi Ranjan Kumar. The title of the work is Nonlinear Impact Time Guidance with Constrained Field of View. So why is this work important? First of all, in realistic scenarios, you might often be required to take down a very powerful adversary using very small interceptors. So the need for simultaneous interception becomes very important. That is a salvo attack. So you need a tight control over the impact time. Now, why is field of view important? Often, if you require a very large value of impact time, you might be required to take a detour, thereby occluding the target from your field of view, which might lead to failure of the mission. So both of these constraints need to be met. Now, unfortunately, in the literature, not much work has been done to address both of them simultaneously. And this is the gap that we look to plug in through this work. So this is the standard engagement kinematics that is given by the stationary target and the intercepting missile. The objective of the guidance is, as I have already mentioned here. Now, our strategy is to have a two-phase guidance command, the first phase of which comprises a deviated pursuit strategy, and the second phase is cooked up using a Barrier-Lyapunov function, which looks something like this. There are two control parameters here, T star, which is the switching instant between phases 1 and 2, and the other is C, which is a parameter during the second phase of the command. Now, we have found that the feasible region in the controller space for these two parameters is given by the hatched region here, which is bounded by this segment of this rectangular hyperbola. Why is this necessary? Because our eventual impact time after a lot of derivation comes out to be this, which comprises three terms. If you choose T star to be very large to violate that constraint, then the third phase doesn't even begin. And if you choose your C to violate that constraint given by that hatched portion, then your terminal lateral acceleration and your terminal deviation angle, neither of them go to zero. In fact, they can be pretty high. So in the course of the next few simulations, we'll highlight these points as we go on. So this is a typical case where the desired impact time is 23 seconds and you've chosen a T star of 10 seconds. And you can see we have respected those constraints on the parameter space and eventually leading to zero deviation angle and zero terminal lateral acceleration. On the other hand, if you violate the constraints on C by choosing C to be less than C crit, then what happens is you still achieve interception, but the terminal deviation angle, neither the terminal lateral acceleration go to zero at the terminal phase. Similarly, if you respect now this bound on C, then all the three phases are visible here. The last segment is a straight line, and you end up with a zero deviation angle towards interception and a zero lateral acceleration as well, which is a desirable scenario. Similarly, if you play around with T star to violate that constraint by choosing a very large value of T star, you don't have a straight line segment as opposed to smaller values of T star, where the last phase is basically a straight line. Again, if you relax or contract the field of view constraint by choosing delta m to be between 50 and 85 degrees, you see that the detours have become larger or smaller respectively. There's lots more to say about this. We invite you to go through our paper, and in case of queries, please feel free to drop in an email. Thank you.
Hello everyone. Today I'd like to talk about our recent work on disturbance estimation and injection for aircraft glide slope regulation and atmospheric turbulence, and we used an approach based on matrix sums of squares programming for this. I'd like to acknowledge my co-author, Professor Shali Bai, with whom I wrote this paper. Typically for aircraft landing problems, there are two major challenges for landing control design, namely atmospheric turbulence that includes discrete and continuous wind gusts and wind shear. In addition, a fixed glide slope is typically required during the approach and landing phase. Past research has included MPC, H-infinity control, and disturbance observer control. For disturbance observer control, obtaining stable disturbance estimation is critical. This is complicated for the flight control in turbulence since the wind disturbance is coupled to the state dynamics. And in fact, it is coupled through the aircraft pitch and pitch rate. We consider longitudinal dynamics of the aircraft under disturbance D, containing horizontal and vertical wind, as well as aerodynamic uncertainties. To estimate the disturbance, the following observer dynamics is proposed, where the key variables is the auxiliary vector P of x and the gain matrix N of x. The auxiliary vector must be chosen such that the disturbance estimate quickly converges to the input disturbance and then can be used in any compensation control scheme. Using Lyapunov analysis, we show that the synthesis of this disturbance observer actually reduces to solving this following feasibility problem, which is nothing but a polynomial matrix inequality in this case. And these polynomial matrix inequalities can actually be solved using conventional sum of squares programming. For the case studied, we see that the disturbance to state mapping G2 of Z is in fact quadratic, and we propose an auxiliary vector which is a cubic monomial. After solving the following PMI, we find that the gains N of Z and vector P of Z in fact result in exponential convergence of the disturbance estimate, and the results are shown here. These are computed using the Sedumi semi-definite programming solver. If you look at the results, the wind estimate exponentially converges to the actual wind disturbance. In addition, the aerodynamic uncertainties also rapidly converge. The glide slope and the vertical and horizontal wind speeds converge back to their trim states within the first 15 seconds. Hence, we are able to show that disturbance estimation is possible and can be used with any conventional nonlinear flight control scheme such as dynamic inversion. Please refer to our paper for further details on the stability of the disturbance observer. Thank you.
Hi, my name is Ludwig Dose, and I'm a master's student at KTH Royal Institute of Technology in Sweden. I spent last summer working at Caltech with postdoc Petter Nilsson and our supervisors, Professor Aaron Ames and Professor Richard Murray. We used an analytical approach to characterize maximal control invariant sets for integrator systems, and we're able to use these sets to achieve obstacle avoidance for the high-dimensional quad-order system. Despite the simplicity of the single-input integrator system of order n with input and state constraints, it is non-trivial to find the corresponding maximal control invariant set. In general, a set C for a dynamical system of order n is said to be control invariant if there is an input u such that if x initially belongs to C, then x will belong to C for all times. To represent the set C, we use superlevel sets G, which are positive within the set and negative otherwise. In our case, the characterization of these control invariant sets through the G functions was made using a polynomial-based analytical approach, as this would result in a light computational footprint. Our method to guarantee invariance was based on analyzing each state element's evolution with time, investigating where maximal input would be needed, and thus constructing a G function for each constraint, and finally combining these. For example, this control invariant set is obtained for triple integrator. In essence, our method is based on finding roots to polynomials, which is challenging for large dimensions. Fortunately, however, there are analytical solutions for degrees less than 5, and real-world systems seldom contain integrator chains of higher order. In this paper, we utilize the corresponding control invariant set for n equal to 4 to control a 12-dimensional quadorder. We use the model presented here, where the important parameter that we have time to discuss now is the position vector r. In fact, using differential flatness, we're able to rewrite the system in terms of r and its derivatives only. And look, we can identify this as our fourth-order integrator system. The key idea behind our approach is then to do obstacle avoidance in flat space, that is on the integrator system. In other words, we use the integrator's control invariant set as a safety filter to potentially modify the quadorder's input u desired in order to not collide with other objects. Using the sim-mechanics environment in Simulink, the quadorder was assigned a track to follow. When the safety filter was turned on, it also had to keep a minimum distance to the center of the red sphere. And as we can see in the videos, we here successfully demonstrate set invariance based on analytical expressions being used as a safety filter, which achieves obstacle avoidance. With that, I would like to thank you for listening, and I hope to see you during the interactive session.
My name is Pedro Casal, and I will be presenting the work that I did in collaboration with Rita Cunha and Carlos Silvestre titled Improved Maneuverability for Multi-Rotor Aerial Vehicles Using Globally Stabilizing Feedbacks. The multi-rotor model that we consider in our work is one where the thrust and angular velocity are inputs and the vehicle has the capability to invert the direction of the thrust. The Blade 200QX quadrotor seen to the right is an example of such a vehicle. Multi-rotor vehicles that can perform thrust reversal are able to track reference trajectories both upright and upside down. In our work, we present two hybrid controllers that render the zero tracking error set globally asymptotically stable, as well as semi-globally exponentially stable with and without thrust reversal. In particular, we follow a hierarchical design approach, which starts with the stabilization of the position subsystem. We start from two earlier contributions on global asymptotic stabilization through saturated feedback and semi-global exponential stabilization through linear feedback, and combine them in our paper to achieve both properties simultaneously. We extend the controller for the position subsystem to the full multi-rotor dynamics through hybrid backstepping. Our controller is particularly well suited to throw and catch maneuvers, which typically consists of a combination of open loop maneuvers between equilibrium points, called throws, and locally stabilizing feedbacks. An example of a throw in the multi-rotor case consists of an open loop rotation between equilibrium points. If the vehicle has thrust reversal, then we are able to catch it upside down. The controller proposed in our work improves existing throw and catch for multi-rotors because one does not need to worry about landing within the basin of attraction of a local controller because catch controllers are global. Here you can see some simulations of the closed loop system with and without thrust reversal. The throw maneuver consists of a half flip. As you can see, when thrust reversal is available, the vehicle can quickly come back to the origin. When thrust reversal is not available, the vehicle drops significantly in altitude because there is a period in time in which it accelerates towards the ground before recovering to the upright configuration. We have also done some experiments which demonstrate the ability of the proposed controller to perform the half flip maneuver for the Blade 200QX quadrotor. You can find the code for the figures in the paper at my GitHub repository. Thank you for your attention.
My name is Rohit Kumar, and today I am going to present my paper titled Quaternion Feedback-Based Autonomous Control of a Quadcopter UAV with Thrust Vectoring Rotors. This slide shows the dynamic model of the tilt rotor UAV, which has been investigated in this paper. It includes the force equations, the torque equations, and the kinematic equations governing the motion of the UAV in three-dimensional space. The top-level overview of the flight controller is shown here, which includes the position controller, the attitude controller, and the control allocation for the system. Full-state feedback is utilized for closed-loop control. First, I'm going to talk about the attitude controller. The attitude control is derived by linearization about the hovering condition of the UAV, which means zero roll, pitch, and yaw angles. It also includes zero rotor tilt angles. The rotational dynamics of the UAV are formulated as a state space shown here, and an accurate control allocation for the system is derived. Here, the control architecture of the attitude controller is shown. It should be noted that first, the error quaternion is computed, and then it is utilized through a PD controller to generate control commands. The desired error quaternion is always a unit quaternion. We also carried out the Lyapunov stability analysis of the attitude controller, and we found the system to be globally stable. Here are some results for time domain analysis of the attitude controller. The UAV is commanded via roll, pitch, and yaw step inputs, and the system responds as desired. Now I am going to talk about the position controller. This is the outer loop which generates commands for the inner loop. The position controller is a PID-based controller as shown here. The complete control architecture looks like this. The updated control allocation matrix is shown on the right side. This slide shows a simulation for waypoint navigation. The UAV is able to navigate across all waypoints using the proposed quaternion feedback-based flight controller. The variation of flight parameters is also shown here. To conclude, we presented the complete control of a tilt-rotor UAV using quaternion state feedback. The derivation and Lyapunov stability analysis of the attitude controller was shown. The position control loop was implemented to facilitate waypoint navigation. The results were shown via numerical simulations, and the future work will involve experimental validation of the proposed flight control system. Thank you.
Hello, I am Zhuang Kang, a master's student from Georgia Tech. Today, I'd like to introduce a novel quad-rotor controller designed with my advisor, Dr. Sudey, and fellow Georgia Tech master's student, Chase Urschel. Many linear velocity or position quad-rotor controllers today have attitude limitations. These limitations are mainly due to singularities that occur either at the attitude control or translational position control level. The presented novel controller attempts to tackle these issues and achieve a globally stable controller with no attitude limitations whatsoever. The controller utilizes a combination of feed-forward and feedback control to remove singularities during translational position or velocity control. More importantly, the controller is quaternion-based, which eliminates singularities from attitude control. The controller is a dual-loop PD-PID nonlinear controller, where the outer loop controls the linear position or velocity and the inner loop controls the quaternion attitude. The novelty of this controller can be seen in the way the two control laws are linked, in which the desired thrust vector UD obtained from the position control law is converted into the error terms used in the inner attitude control law. The conversion is done as such. This simple conversion eliminates most singularities and allows the quad-rotor to fly with little attitude limitation. The Lyapunov analysis shows that the gain lambda q, which is used to obtain the reference angular velocity, is key to achieving global exponential stability. Even so, there still exists other singularity issues such as the vanishing thrust vector and 180 degrees rotation. These issues were solved in different ways, which can be found in more detail in the paper. These simulation results show the response of the quad-rotor under three different types of inputs. First, it shows a simulated step response, where a velocity was given in one direction, then in the opposite direction. Next, the response showed the quad-rotor following a sinusoidal velocity trajectory. Finally, the quad-rotor is flipped by following a certain velocity trajectory. Next, we have implementation results from an actual quad-rotor maintaining zero velocity and undergoing step and sinusoidal velocity trajectories. As can be seen, the controller can be successfully implemented with fast response and accurate tracking. Today, we introduce a globally exponentially stable controller. By adding a variable gain lambda q to a dual loop control schematic, a globally exponentially stable controller can be achieved. The results show that the presented controller can both be simulated and implemented with fast response and accurate tracking. Thank you for listening.
Good morning, everyone. My name is Daniel Wagner, and here today I'm going to discuss measures and LMIs for lateral F-16 MRAC validation. So here's the model in question. It's an F-16 Dutch roll model with some uncertain polynomial dynamics inside of it taken from one of Lavretsky's papers, and it's subject to nominal and adaptive feedback right here and the standard assumptions for MRAC, and here's all the tuning parameters we use. For the theoretical preliminaries, I refer you to the paper that we submitted in. And what we're going to mainly do is that we're going to use our software, Glaptopoly 3, and an SDP solver such as MOSEC to come up with a verification and validation scheme using this objective right here. And it is as follows. We want to find the initial state maximizing the normal of the terminal state, namely beta and phi, given a command signal, which is just the roll angle command input, and a terminal time t is equal to 10 seconds. And we also use this concave quadratic term. And what we're going to do in the end is we're going to compare our results to those obtained using Monte Carlo. We use a normalizing matrix D inside of Galactopoly 3 to avoid ill-posedness. And with that in mind, we can finally state our control validation problem. If we can certify that for every chosen initial state X naught, such that all trajectories remain bounded until they reach a final state belonging to the set, which is just a smaller target for our cost, then the control law is validated. To do this and to deal with so many states inside of our system, we actually we approximate the aerodynamics. And we also include a piecewise disturbance where the control effectiveness drops off significantly at high roll angles. And we use 2 cases of phi max right here. So here are our main results. We did this for both the LQR and the LQR plus MRAC. And as you can see, we get the same upper bounds roughly for both our Monte Carlo and our Galactopoly 3 plus MOSEC framework. And this is good. But when phi max drops off considerably, we see that our LQR upper bound is now much larger. And what happens here is that 2% of the trajectories inside of our system are considered unsafe where they depart because of the drop off in control effectiveness. And what we see here is that this is also reflected in our LQR results in Galactopoly 3 and MOSEC. And the good news here is that we can accomplish this using one run instead of hoping that we have enough coverage of our state space using Monte Carlo to detect this right here. And as we can see, our LQR plus MRAC results are good upper bounds. So finally, we can state our conclusions. We validated a nonlinear F16 plant with both LQR and MRAC. We exploited sparsity for ODEs using parsimony to reduce problems with scaling. And these results were compared to those obtained using Monte Carlo. Thank you for your time. If you have any questions, please do not hesitate to ask.
Hi, my name is Audrey Channen. I am a PhD student under the supervision of Jonathan Dumont, Nassim Meslem, and Ahmad Abli, and I'm going to present my work on takeoff and landing of an airborne wind energy system using a multicopter. In the strongly emerging field of airborne wind energy, development of a control solution to the problem of takeoff and landing is a key to success for this new technology. The solution presented here is to attach a drone to the system, which will allow to take off and landing even in the absence of wind. Here is a scheme of the global system with the on-ground station, the tether, the wing, and the drone. The particularity is that we have the drone as an actuator, but we can also use the aerodynamic forces due to the wing. The objective is to design a controller to control takeoff and landing, maintaining the tether tension. To do that, we have 3 control variables: the winch torque, the drone thrust, and its inclination angle phi. Here is the control architecture, which involves an output feedback linearization method. This method allows to transform a nonlinear tracking problem to a stabilizing one. And once we have a linear problem, we can compute an intermediate linear controller. An important thing to notice in this scheme is that the tether length R is controlled with the winch and the forces UR, and the elevation angle beta and tension force of the tether by the drone and its radial and tangential component UT0 and U beta. The controller was then tested in simulation on scenario including a takeoff and landing under a wind of 2 meters per second. The configuration studied here corresponds to alpha u equal to 0, meaning the wing is always horizontal. However, other configuration can be studied. We obtained the following trajectory, and we can also see on this video the forces acting on the system. The system follows well the desired trajectory, even if there is some oscillations due to the wind. We can also look at the evolution of the tether length or and the elevation angle beta and see that the results are quite satisfying. And those 2 figures show that the controllers allows to take off and landing on this scenario. Thank you for your attention. If you want more information on this work, you can see the paper. And if you have any questions, don't hesitate to send them by email. Thank you.
Hi, I'm Chu Xuanzhi, What I'm going to present is a joint work with my supervisors Pedro Gazal and Carlos Silvestri. The title is Global Trajectory Tracking for Quadrotor through Event-Triggered Control, Synthesis, Simulations, and Experiments. Traditional feedback controllers are implemented digitally in a periodic fashion. To achieve stability, the fixed sampling interval delta t is chosen to be sufficiently small so that the sampled input is arbitrarily close to the computed input. However, this so-called time-triggered control may lead to redundant samples, which are not actually needed to achieve the desired stability property. Moreover, redundant samples are not favorable when, for instance, the communication channel has limited bandwidth or the controller has limited computational power. Using event-triggered control, a sampling is issued only when some state-dependent event-triggering conditions are met, therefore reducing redundant samples. In our work, we particularized this idea in the problem of trajectory tracking for a quadrotor. Specifically, a globally asymptotically stable hybrid controller is given at first, and we are aware of a Lyapunov function that is strictly decreasing with time outside the zero tracking error set. The sampling of this controller is executed at each instant. Now, if we choose the event triggering condition that enforces a slower rate of decay of the Lyapunov function, then a sampling not satisfying this condition may not need to be executed at that instant. Although the synthesis of the controller guarantees global asymptotic stability of the zero tracking error set, it may induce the problem of Zeno behavior of solutions. Generally, Zeno can be understood in the following way. The time derivative of the Lyapunov function tends to zero when approaching the zero tracking error set. Then it becomes easier to fulfill the event triggering condition. Instantaneously, Zeno can be understood in the following way. Some initial state in the zero tracking error set always satisfies the event triggering condition so that it keeps updating at time zero. To enable digital implementation of the controller, we need to eliminate the Zeno behavior. Our way is to restrict the event triggering condition and inflate the zero tracking error set, so that we avoid the accumulating events and achieve the global practical asymptotic stability of the zero tracking error set. We tested our controller on inverted flight of our quadrotor. It is clear from the results that, although the sampling of the actuation signals is aperiodic, the tracking error tends to decrease with time. I'm looking forward to discussing the paper further with you in the upcoming interactive session. Thank you.
Hello everybody, welcome to the rapid interactive presentation of our paper. My name is Frederik Puhalska and I'm going to talk to you about fault-tolerant control for hybrid UAVs. So, this is our configuration, which is basically a combination of a typical fixed-wing aircraft with wings and a pusher motor and a multicopter with additional rotors. This aircraft is able to vertically take off and hover, but also achieve high airspeeds during cruise flight. But another very interesting property is its inherent overactuation, which means that we have more actuators available than we actually need to control the rotary degrees of freedom of the system. And this is something we're going to use for fault-tolerant control. So here you can see our controller setup, and this adaptive controller consists of an integral sliding mode part and a control allocation module, which distributes these virtual controls amongst the actual physical actuators. And as soon as an actuator fault occurs, a fault detection and diagnosis module informs the controller, and then the control allocator redistributes these virtual controls amongst the remaining healthy actuators. For controller design, we assumed linear plant dynamics, which also consider fault effects in these primary actuators B1. The control allocator itself has been implemented using a pseudo-inverse based approach, and the sliding mode controller consists of a linear state feedback part and a nonlinear part, which is needed to ensure sliding motion. To reduce the chattering effect of this switch-like behavior, we had to approximate it by a sigmoid-like function, which you can see here. So, and to test our UAV flight controllers, we built a hardware-in-the-loop demonstrator, which incorporates a RC servo as well as an PICSOC 4 flight controller, which is also used in the actual aircraft. Here you can see a diagram of our hill setup, which has a speedcode real-time target machine at its heart. So now I would like to close with some simulation results. The first scenario is an elevator lock-in-place failure, which you can see here. And the elevator gets stuck in this